Hello everybody. Today I will be talking about a recent piece of work that we've been conducting on unsupervised approaches to decomposing activations into features. This work has been done as part of the Not to Die research team, which has been supported by Sir Matt. Now the main question we want to ask is, given a set of activation vectors, how can we linearly decompose them into feature vectors? Now, we think this matters because what we try to do in interpretability of neural networks is to try and find out what the exact features are that these neural networks are using to do their computations. In other words, we want to know which features it learned and which ones it's relying on in order to make its predictions. Now, one background assumption that we will run with throughout this talk is that activations are linear combinations of features. In mathematical terms, you can see this expressed on the right-hand side. Each activation vector is a linear combination of coefficients and features. Now, the question that we're interested in is, given these activation vectors, how can we find the features? We identify an important distinguishing factor in our work and want to propose the following framing. Are there more features than the dimensions of the activation space, or are there less? Let's first explore the case in which the number of features is smaller than the dimension of the activation space. In the case where we have less features, we could in theory give each feature an orthogonal direction in activation space. Now, that would mean that our features are linearly independent, and that might make it quite a lot easier to find features. If we are in this regime, there are a bunch of linear algebra methods that we can employ to solve for these features. Now, to highlight a few, I would like to show you SVD first. In SVD, we have the following optimization problem. First, we have an outer loop that minimizes over the features. We want to find the best features that minimize this expression. And in the inner loop, we want to minimize over the coefficients. Now, you can see this term here, and this is exactly the assumption that we were making in the beginning. This is where we attempt to reconstruct the activation by multiplying our feature vectors with the weights. And this here is just a simple mean squared error term where we want the error term to be small. Now, one quite similar thing that we can do is called non-negative matrix factorization. The only difference between this and SVD is that now, instead of minimizing over all features and coefficients, we assume that these are non-negative. This assumption makes quite a lot of sense when we look at neural networks that have value activation functions, where every number smaller than 0 gets cut off. Now, a different solution method is PCA. We again see the similarities in the optimization problems. The only difference is that we subtract the mean of the activation vectors from the activation vector at first. In our work, we're particularly interested in the case of non-negative matrix factorization. If we continue to look at this case, we can simplify it and denote the activation and the reconstruction of the activation in matrix form. Now, if you look at this formulation, this is the very same as the one above. The only difference is that we replaced it with matrices. The F you can see here is a short form for the Frobenius norm. If we simplify this further, we arrive at the following picture where NMF helps us reconstruct the activation vector roughly by a tall matrix of coefficients and a wide matrix of factors. To see non-negative matrix factorization in action, we look at a paper that implemented this on a problem. In the paper Acquisition of Chess Knowledge in AlphaZero, DeepMind uses non-negative matrix factorization to see what the neural network pays attention to and what it has learned in the game of chess. Let us have a look at the architecture of the network first. We can see that the network in the paper takes in a board state, it feeds it through a ResNet 50, and then there's a policy head and a value head. This is the standard AlphaZero network. So far so good. Let us zoom in on the ResNet 50 to see how a block of the ResNet is constructed. Now the input goes through an 8x8 by 256 filter. Now, one ResNet block consists of the activations, a skip connection, and a bunch of values and convolutional neural networks. This gets repeated 20 times, and we can extract the activations at each position. So for each of these 20 blocks, we can extract an activation tensor. If we zoom in on the activations, we can see that the 8 by 8 dimensions refer to the 8 by 8 dimensions of the chessboard. Now the 256 is just the dimensionality of the activation vector that we want to extract and decompose. We have looked at the architecture now. Let's have a look at the data set of activations. The way we construct the activation matrix is simple. We pick one of the network's 20 ResNet blocks to analyze. After that, we sample 1,000 game states at random. We extract the activations from our block after feeding in the game states, and then we reshape and stack activations to obtain the matrix. Now, you can see this in action here. We sample 1,000 random game states, put them through the network, extract the activation vector at a given state, and then reshape those to obtain a 64 by 256 dimensional matrix. We then stack these together to obtain this large, tall activation matrix. After obtaining these activations, we will want to apply NMF to extract the coefficients and the features that we're interested in. In this case, we're limiting the number of features that we want to obtain to 36, and hence you will get the according dimensions of your matrices. Now, how do these results look like? Let's actually look at the coefficient matrix and try to visualize what's going on here. Mind you that this tall matrix is composed of 10,000 game states that were chessboard states of the shape 8 by 8 that we reshaped from 8 to 8 to 64. Now, if we want to visualize a board state and what the neural net is paying attention to, we can extract this game state by taking the 64 rows that correspond to the game state and reshape it into 8 by 8 again. And what we'll get is something like this, where we can see that for this particular game state, the neural net is paying attention to right diagonal moves of the bishops. Okay, now that we've looked at a few feature case, let's look at the many feature case. Again, note that the distinguishing factor was whether we have more features than the dimension of the activation space. In the many features case, we expect the network to have learned a lot of features so that it cannot fit the features in the activation space and give each one of them a orthogonal direction. Now, this makes it quite a lot harder to interpret the directions. Some of you might know this phenomenon as superposition. In the literature, we found an attempted solution to this problem, which is that of sparse autoencoders. And the paper that we would like to use as a case study here is called Taking Features Out of Superposition with Sparse Autoencoders. Let us have a first look at the setup for generating the activation vectors, similar to what we did in the previous paper. Now, in the previous paper, we had access to activation vectors just by taking board states and feeding them to our network. Now, in this paper, we don't quite have that, but we are generating activation vectors ourselves. To do so, the authors define truth features at first, before constructing a sparse ground truth feature with the coefficients, and then generating the activations. The way that they define the ground truth features is by sampling from a uniform h-dimensional sphere. What we get when we perform this operation a few independent times is the feature vector here, which is basically one that contains the ground truth features as rows. And those we will later want to recover with the sparse coding method. To arrive at the activation vectors, we also need coefficients to multiply with our features. The first step in constructing these coefficients is to sample from a Bernoulli distribution, where the probability of 0 is very high and the probability of 1 is very low. Now, we want to do this because we want to ensure that the feature vectors are multiplied with coefficients that are very sparsely activated, so that on average, the vector that we get here only has 5 active features. Now, a side note here, to emulate the properties of features in real data, the authors of the paper correlate the probabilities with each other and vary the frequency with which they occur. Now, after obtaining the sparse vector, the authors choose to scale it with a vector that has the same shape, but is sampled from a uniform probability distribution between 0 and 1. If we apply the Hadamard product of these two vectors, we will obtain the sparse ground truth feature coefficients with which we can now multiply our feature vector to arrive at the data set of activations that we initially set out to create. To get these activation vectors, the last step is quite simple. We multiply the coefficients with the features and we get the activations. To recover these features from activation vectors, we will want to use sparse autoencoders. Now, what is a sparse autoencoder? A sparse autoencoder looks like so. It is basically a simple neural network that has an input layer and an output layer of the same size. And then in between, there is an intermediate layer that is quite a lot wider. The input to a sparse autoencoder will be the activations, and what we want the output to be is a good reconstruction of these activations. What makes this autoencoder sparse is that we apply a penalty on the weights between the intermediate layer and the last layer. Okay, cool. Just terminology note. The set of weights in between the last layer and the hidden layer is what we call the dictionary. And this is what we want to use to approximate our features. Now, during training, we want to incentivize the sparsity of the dictionary. We do so by using the following loss function. The loss of a given activation will be a reconstruction loss plus an L1 loss. The reconstruction loss is a simple mean squared error loss that you can find here. And the L1 loss attempts to incentivize sparsity by making the absolute value of our coefficients small. Again, the main goal here, if we contrast this to the previous case, is to reconstruct the activation vectors, which is done with the coefficients matrix and the dictionary, in which we can find our features. Now, in order to measure whether we have actually recovered the features that we constructed in the beginning with the dictionary that we're learning, we will use something called the mean-max cosine similarity. And it looks like so. We take the average cosine similarity of the feature vectors and the corresponding feature in the dictionary that maximizes the cosine similarity. And the way you would interpret this is if the dictionary contains a feature that points in the same direction as the original features, then the cosine similarity will be high, and otherwise it will be low. And so what we hope for in the best case is a mean-max cosine similarity of 1. In the worst case, we will have found a mean-max cosine similarity of 0. With all that, let us have a look at the experimental results and the hyperparameter tuning. What you can see here is a plot between the L1 penalty coefficient, which is basically the alpha in our loss term that we were showing earlier, and the mean-max cosine similarity. What I want to draw your attention to is that this is on a log scale and that there is quite a large range for a good L1 penalty coefficients. Now, mind you, the L1 penalty coefficient alpha will determine how much you incentivize sparsity. The higher the penalty, the higher the loss term will be, and so we'll get more sparsely activated features. On the other hand, here you can see a plot of the mean-max cosine similarity and the size of the learned dictionary relative to the ground truth. So what we can see here is a plot of the mean-max cosine similarity for different learned dictionary sizes. And as we can see, as the learned dictionary approaches the correct size, that is, the size where the dictionary has as many features as our original set of features that we constructed, we'll be able to recover a close to 1 mean-max cosine similarity. And that's what we would expect. As we continue to grow the size of the learned dictionary, the performance gets a little worse. So what we want is to be in this regime where our mean-max cosine similarity is high Lastly, the interplay between the L1 coefficient and the size of the dictionary is also quite important. And as we can see here, this whole yellow region indicates the region where, for a given size of the dictionary and a given L1 coefficient, we will have the maximum mean-max cosine similarity. A question that the authors asked themselves after conducting these experiments on the toy example was how to tell if the hyperparameters they choose work for real models. To answer this question, I want to draw your attention to one particular method that the authors used. This method makes use of the presence of something they call dead neurons. Now, if we take a closer look at the sparse autoencoder and zoom in on the neurons, what makes a dead neuron is the following. A dead neuron is basically a neuron that never activates. What do we mean by never activate? Well, a neuron that never activates is simply a neuron whose activation value is always 0. The reason for there being dead neurons can be twofold. One reason is that the dictionary that we're learning is simply too large. The other reason is that the L1 penalty coefficient alpha is too large. In the first case, think about it this way. If the dictionary has just the right size, that is, the dictionary is just as large as the amount of features we have, then it can store one feature per entry in the dictionary. Now, if it's way larger, we expect there to be a lot of free space, hence dead neurons. In the second case, when the L1 penalty coefficient is too large, we expect dead neurons to occur too, because we can regulate the amount of sparsity that we want with our L1 penalty coefficient. If the coefficient is too large, we will never ever have any active features in our dictionary. And so dead neurons also make sense in this case. This is just a simple heuristic we can use in real models where we actually don't know how many features the network has learned, and we need to adapt the dictionary size or the L1 penalty coefficient to train our sparse autoencoder. Let us finish today's discussion with a brief overview of what we did. We presented a case for looking at interpretability methods along the central axis of whether there are fewer features than the dimension of the activation space or more features. In each case, we were able to identify a few methods that have been proposed to solving for the features given a set of activations. We're currently looking at whether there is more supporting evidence for this in the literature and which other papers explore similar ideas to the ones that we presented. Now, one potential pitfall is that the assumption we're making in the very beginning about the linearity of the activations is false. What we are interested in to find out here is whether there are ways that this picture could be completely confused, meaning that activations are not linear combinations of coefficients and features. If we live in a world where that is true, we would basically have a much harder time figuring out features from a given set of activations. With that, I want to finish today's session and invite you to leave a couple comments in the section below to discuss what you think about this framing. Thank you very much and see you next time.